Okay, well, good morning. How's everybody doing? Good? Are you liking the convention so far? Awesome. Who's tried college yet? Everybody tried college yet? I've heard a lot of really good things about college yet. Okay, well, my name is David Wollmer, and I'm the For Life Chief Scientific Officer, and I'm really excited for this session here because you're going to learn about transfer factor. Who wants to learn about transfer factor? Well, before we start, I want to ask the question. Why are we here? Why are you here? Why did you come to this workshop? To learn, right? To learn about transfer factor. And where do you learn about transfer factor? At a For Life convention, right? That's why we're here. We want to learn about transfer factor because transfer factor is really what differentiates us from everybody else, right? Nobody else has transfer factor like For Life. And so you're here to learn about that because when you go out and you talk and you spread the word about For Life and transfer factor, you have to be educated to do that, right? And education is a really important process, part of the process. Okay? Just like your immune system, right? Your immune system has to be educated, so do you. So before we start, I want to ask everybody to rise, stand up, rise. Everybody rise. Everybody stand up. Okay. Now, I'd like you to do something really simple. Talk to the person next to you. Talk to them. Communicate with them. Tell them, if you don't know them, tell them your name. Tell them where you're from. Tell them what For Life products you like. This is wonderful. What are we doing? What are we doing right now? Okay. Are we done? Are we done communicating? Okay. You can sit back down now. So. Okay. All right. So what are we just doing? You were communicating, right? You were communicating. You were talking to someone. You were communicating maybe a message, a little bit about yourself, what's important in your life, right? Communication is so important to us as people, to us as a society. And guess what? Communication is also important for our immune system, right? Our immune system has to be able to communicate, right? And so this little exercise that you just did, it was about communicating, right? Getting to know someone. And if you think about it, right, you're kind of like a transfer factor, right? You're communicating with people, right? Just like transfer factor communicates with immune cells. And we're going to learn a lot about that today, and we're going to have a little demonstration at the end of it to kind of build off of that and show how transfer factor is a communication molecule. Okay? Is everybody with me? Okay. So here's the lineup. We're going to have 4 different parts. Part 1, we're going to learn about the immune system. Dr. Tori Parker is going to come up and tell us everything we need to know about the immune system. Then part 2, Dr. Brett Vaughn is going to come up and tell us about the history, the discovery of transfer factor. Way, many, many years ago, when transfer factors were discovered, and Dr. Vaughn is going to talk to us about that. And then I'm going to get back up and I'm going to tell us, how does For Life get their transfer factor? Why is it different? How do we study it? How do we characterize it? And then after that, part 4, Dr. Paul Brock's going to come up and tell us, how does transfer factor work? Right? Does that sound good? Does that sound like a good agenda? Okay. And then after that, this is the fun part. We are going to graduate. Right? It's like you're at college, right? So on your chair, you should have a certificate, right? That's like your diploma, right? And on that, with that diploma is what? What's with that diploma? There's a pen. And so that pen is going to be like your cap. And so at the end, we're going to graduate. We're going to put the pen on, right? We're going to put that pen on. And then what I want you to do is I want you to take a selfie of that pen. Okay? All right, has everybody got their pen, the little pen? Yes! Okay, don't put it on yet. Wait till we've graduated, right? We don't want to graduate early. Okay? Does that sound good? Okay. Well, thank you so much for coming here. I hope you guys get a lot out of it. And We're going to have the next speaker.
Ladies and gentlemen, please welcome to the stage, Dr. Tori Parker.
Good morning, everyone. I heard a lot of excitement from Dr. Wollmer this morning. Are you guys ready to begin our session today? Wonderful. I'm so excited to be our first presenter this morning. I get to talk to you all about the immune system. Are you excited to learn about the immune system?
Yes.
I think it's a fascinating process in the body, and it's a great opportunity today for us to all become more expert in our understanding of the immune system. So this is part one of the 4 parts in our series this morning. So the first part we will focus just on helping you understand a little bit more about how your body works. So I'll be introducing you to the different parts of your immune system, as well as giving you the opportunity to understand a little bit better how your body responds to something that could invade your body or cause problems in your body. Teach you how your body reacts to those invasions and how it protects yourself and the different ways that the body does that. And finally, we'll talk about a little bit about how the body recognizes what is supposed to be you and what is not supposed to be you. And our bodies have very specific, really powerful ways of understanding how that works. So that's our goal today, and I hope that you are able to understand those 4 pieces as we move through our discussion today. All right, what is the immune system? It can be defined in very simple terms. First, it takes care of anything that it tries to keep anything out of your body that shouldn't be in it. So what are some of the ways that we do that? You have skin, right? We can cough, we can sneeze, we can get things out of the body and keep them from getting in. So that's the first basic part of the immune system. And the second way that we think about it is anything that does get in, we have really powerful ways of taking care of that and helping our body recover and get well again after something does get inside of our bodies. So does everyone understand the basics of the immune system? You know what it is now? Are you with me? Yes. Great. All right, let's just keep going a little deeper. This is your turn to interact and understand and learn about your immune system. So everyone, I want you with me. I want you to point on yourself each of these organs as we learn about them. Okay? So let's start at the top of our display right up here. The first 2 that you see up there are tonsils and adenoids. Okay, so everyone, here's where your tonsils are. You take your finger. Your tonsils are in the back of your throat. Okay? Tonsils. Okay, now how about the adenoids? Sides of your nose. Back in your sinuses, up by your nose. That's where you find your adenoids. Okay, everybody found those so far? All right, now lymph nodes, the next one you see on the display, those are all over your body. So we don't have a specific place that we can point to those, but just like you have blood vessels, arteries, and veins, you also have lymph nodes and lymphatic vessels that travel throughout your whole body. So those are all over. The next one down is called the thymus. This is a gland right in the top of your chest, right behind your breastbone, right here. So if everyone just points to the top of your chest, that's where your thymus is. That's an immune organ. It's just above your heart, just behind your breastbone, right here in the center of your chest. Now, everyone reach to your left side, right down here at your ribs. There's an organ there called the spleen. All of us have a spleen, and that's an important immune system organ as well. Okay? Now on your gut right here, you have your digestive system. We'll talk a little bit more about that because that's really important to our immune system. But we have a lot of important aspects of immunity found within our bowels, our intestines, in the gut part of your body. All right, and the last one, this one's, you think about some of the large bones, like in your leg. This is where you create some of your immune cells. It's right in the bone marrow, down in the bottom, inside of the bones. And that's where some of our cells we're going to talk about in a minute are created. All right, does everyone know where your immune system organs are located now? Can you raise your hand? Everybody got it? Okay, should we do it really quick? Okay, we're going to play a game. Ready? Everybody point to your thymus. Okay, point to your adenoids. Oh, you're a little slower that time. Okay, point to your bone marrow. Good. Okay, point to your tonsils. Back of your throat. Everybody got your tonsils? Okay, here's a trick question. Point to your lymph nodes. Everywhere. We've got lymph nodes all over. We've got lymph nodes everywhere. Good job. Okay, and the last one, an easy one again. Where is your intestine? Good. Nope, there's one more. What did I miss? Here's a trick one. What did I miss? Not muscle. Spleen! I heard it, the spleen! Good job! Where's the spleen? Right under your ribs, right on your left side. Good. Okay, you got it! You got it! You now know where all of your immune system organs are located. Good work. Alright, let's go on. I'm excited to tell you a little bit about the intestines. Okay, now this is an important fact. 70% of your immune system is found in your digestive system. Everybody repeat that after me. 70%. Ready? 70%. Why? Why is 70% of your immune system in your gut? Here's some good answers out there. Where do we put most of the foreign stuff that we take into our bodies? Where do we put most of it inside? We eat it, that's right. All right, right on. Took you. Quick answer, excellent. Right through our mouths and our stomach. That's where we eat most of the foreign things that our body's exposed to. So our immune system is always ready to make sure that there aren't any threats or any harmful things in our food. Because that's where we are exposed to most of the foreign stuff that happens in our as we go about our day. So within the immune system, you have these sections you see on there called Peyer's patches. And these are essentially little concentrations of immune cells, and their job is to take a little sample of all of the different things that you eat and make sure that it's helpful and not harmful, and to keep track of what kind of things you're exposed to in your diet, and help your body respond appropriately to that food and other things that are found in that food. So the immune system is constantly being very vigilant about anything that we might be exposed to in our life. Okay. Now, let's talk a little bit deeper. We've talked about the body systems, we've talked about the focus of the cells. Now we're going to talk about the individual immune cells that are found in the immune system. And we'll separate these cells into two groups, and then I'm going to tell you a little, we'll go through a little scenario and learn a little bit more about each of these cells in a way that I hope you'll be able to remember. So these 8 cells that work together, they accomplish 2 main tasks. First of all, as you saw in the beginning, they have to get rid of things that are foreign. They take care of invaders, they take care of bacteria, viruses, and other toxins that we might be exposed to. And the second one, which is also equally important, the immune system takes care of our own bodies. Sometimes something goes wrong in one of our cells. And if something goes wrong in that cell, the body has ways of recognizing that, helping get rid of that cell, and then cleaning up the leftovers, and then a new cell can replace it and help it to recover and build your body back to the way it was before. So 2 tasks, anything foreign and anything wrong. If you can do those 2 things, then you've accomplished a lot of great health. Okay, another important way, and this is how we're going to divide our cells today, is 2 types of immunity. One is called innate immunity. All of us have an innate system that is capable of responding generally to all kinds of threats. And as we learn more about transfer factor today, you'll find that transfer factor fits perfectly into our innate immune system. And the second main task is called adaptive immunity, which is where we are able to respond and prepare against a very specific attack. Some specific organism that we may have experienced in the past will be much better prepared to handle in the future. Okay, so let's talk about these top 6 cells in the innate immune system. So I'll say them once just so you can understand how they're pronounced and get to know them, and then we'll talk about them individually. So on the top you see the neutrophil. Neutrophil, good. Okay. Second one to the right, eosinophil. Good. Eosinophil. Okay. Next one down, basophil. Good. Basophil. Okay. Monocyte. Good. Natural killer cell. And macrophage. Okay, everybody got those? Thank you. Good to hear you repeating them. That's great. All right, so now I want you to imagine you're not in this room at the moment. You're at home and you're preparing a meal. For that meal, you've decided to chop some vegetables. So you've got your knife out, you've got your carrots or your other vegetables, you're chopping your vegetables. Suddenly you hear a noise. And you miss the vegetable and chop your finger instead. Has that ever happened to any of you?
Yes.
It's happened to me a lot. It happens a lot. You get distracted and there goes your finger instead of your vegetable. All right, so let's use the scenario of a cut finger, and I'm going to compare that to an emergency. Let's say a car accident on the road. So each one of these cells, as we talk about them, you can relate to some aspect of an emergency. Because when you cut your finger to your body, that is a small emergency. And it has a very specific response to that emergency. So the first phase of that response is with our friends, the neutrophils. So as you first cut your finger, the neutrophils are the emergency response team. They're the ambulance. They're the first to arrive to that cut. And they're going to come in and they're going to immediately start attacking bacteria that may have been on your vegetables or on your knife or on your finger that now are inside your finger. And they're going to start eating up those damaging things. And there's a lot of these neutrophils in your blood, see, 50 to 70%. And so they get there quickly, they're the first to arrive, they're the emergency medical responders. Now shortly after the emergency begins to occur, we also begin to need to control the damage at the site. So if we had a car accident, what could happen in a car accident? There might be a fire, there might be somebody nearby that got hurt, there might be other cars on the road. So I always think of the eosinophil as the fire truck that's arrived after the ambulance. So the fire truck comes in and makes sure that there's no fires. They immediately kind of start off the allergic response, the inflammatory responses. So you can think of inflammation sometimes like a fire, it helps you remember. And so this one is a smaller circulating, only 2 to 4%, but it begins to kind of block the area, keep other cars from getting into an accident and making sure there aren't any fires in that area. Third, we have the basophil. This one comes along, and normally, when you cut your finger, the blood will start to clot, and then it gets kind of hard. And the basophil comes along and starts to secrete fluid and help you to keep the blood from clotting too quickly so that your full immune response can get there and other cells have a place to work, to keep the fluid there to work. So I think of this as like the police that come along shortly thereafter. The police come in and they put their police tape around and they cordon off the area and they let the detectives come in and investigate the accident. Make sure that there's plenty of room for the investigator to come in and to do their job. So this is in the body means serotonin, histamine-inducing inflammation, some swelling, some redness to help your body recover. Now, along the way, floating around in your cells, you have these cells called monocytes. These are floating around in the blood looking for an opportunity to help. So the monocyte is going to discover, as it floats around, that you've got a cut finger. It's going to go into that space, and it's going to then change into the next cell that we have right here, which is called the macrophage. So the macrophage is like your victim advocate. There's someone that comes in and they help out the folks that were involved in the accident, they make sure they're okay, help them with their recovery, and they stay. The macrophage will stay in the area, making sure that any bacteria or dead cells or injured cells from your knife cut get cleaned up, removed, making room for the skin to heal so that you can recover and have a normal finger again. So that's the macrophage's job. It comes in and cleans up and sticks around until everything's all taken care of. All right, our last cell, I think of the natural killer cell, at least in our example. It does many things, but one of the things it does is it's a great communicator. So the natural killer cells can help us with our understanding what's going on around. It calls in, sends out what are called cytokines, communication signals to other cells. It helps clean things up, helps respond to the threats. It kind of has a job, does lots of different things. But one way that I thought of this is like the dispatcher, the radio control. It helps bring in the fire and the ambulance and the victims advocates and the police, and helps coordinate everything and helps communicate across the board, and it helps clean things up afterwards, so they're always around. All right, how did that work? Do you have a clearer understanding now of how our innate immune system responds? Can you hopefully remember cutting your finger and remember that you have lots of help during that process in your immune system? All right, let's move on now. We'll talk about the adaptive immune system for a minute. This one has two specific cell types involved in it, the T cell and the B cell. So we'll talk about those two now. First up is our T cell. The T cell includes the name T because it is formed in the thymus. Everybody point to your thymus. Good, you still remember. Thymus, that's where it got its name, that's where the cell matures. Now it attacks specifically, so now we're talking about, rather than a normal emergency response, this is more of a very specially trained team of this Navy SEALs or the elite special forces. They can come in and target some very specific activity very effectively. It includes several different types. We're going to not go into those in a lot of detail, but there are helper T cells and cytotoxic T cells, slight differences, and they have a little bit different roles, but their job is to be a very specific response to something that you may have seen before, which is why you don't get the same illness more than once in a time, because of your adaptive immune system. So one way to think about T cells and how they do this job, every cell in your body has markers on the surface of its cell. Likewise, bacteria, viruses, others also have a very specific, unique shape, specific molecules on the surface of them that allow us to tell, is this me? Or is this something else that should not be here? So if it's you, it's called a self-receptor, you see on the right. And it bumps up against the cell and says, yep, that's part of me. Yep, that's part of me. Yep, that's part of me. Well, wait a minute, what are you doing here? And that is not part of me. You are not supposed to be here, so we need now to build a response and do something about it. So that is the primary principle of T cell self-recognition. Now the B cell, part of our delayed or adaptive immune system, gets its name from the bone marrow. Where's your bone marrow? Big bones, right? Your bones in your legs, lots of places. Bone marrow is where B cells mature. So they're produced by antibodies, and they send these antibodies out around the body looking to bind up to things that are not supposed to be there. One of their main roles is part of our memory. Remember we talked about recognize, respond, and remember. Remembering health threats is one of the roles that the B cell has in our immune system. And a way to remember this is to think of it like a lock and a key. So every time a B cell produces an antibody, it's a very specific key that only fits in one door. And so as an antibody is produced, it will only recognize and bind to a specific invader, or one very specific type of something that should not be there. And whenever it recognizes that something's there that shouldn't be, it very quickly starts producing millions and millions of antibodies to allow your body to respond to that threat. And now we're going to take and put it all together. While the innate immune system and the adaptive immune system work independently and have their own roles, they also talk to each other. So the important thing to remember here that this gets even more complicated than this. If you've ever seen immune graphs and charts, they're massive and there's so many different things that happen and we're learning about and understanding how the immune system works. But fundamentally, the innate immune system cells talk to each other, they bump into each other, they communicate with each other in many different ways, allowing you the ability to be healthy, to respond to threats, and to recover when you are exposed to one in your life. The immune system is fascinating and powerful. All right, let's summarize our points today for my portion of our training. First off, the immune system is everywhere, right? We have organs all up and down our whole body. The immune system is innate, where you can immediately respond to something, such as a cut on your finger, and it can be adaptive, where if you got sick once, it makes sure you don't get that illness a second time. Keeps things out, gets rid of anything that gets in, and it has a number of different cells involved in that process, and that allows us to immediately respond and do all the different things that need to happen to recover from that threat. All right. Are we doing volunteers? I think we should. Do I have somebody who wants to come up and answer? I have 2 questions. Raise your hand. Barbara's going to come pick you out. Barbara's right here in the front.
Hey!
So we want somebody who's brave. So wants to see if they can come up. Barbara's going down the middle right here. Looks like we have someone selected who's willing to come on up
70%.
and take our quiz. Do we have someone that can help with the, make sure, I understand some of it, but quick translator? Barbara's working right here. Looks like we have got lots of possibilities. Thank you all for volunteering to come on up. All right, we have two coming up right here. Thanks for your willingness to come and be part of our first folks to be quizzed. Just go ahead, please. You two right here, come on up. Yeah, please. Come on out in the light here for just a minute. Thank you very much. Okay, are you ready for your question? Okay. What percent of immune system is in the gut, in the stomach?
70.
Yes, that's correct. We said 70%. It is a range. You can give me a better answer. Yes. There's one more question. Okay. Name 3 of the 8 immune cells that we talked about.
Neutrófilos, basófilos, eosinófilos, mastocitos, monocitos y
Congratulations, you made almost all of them. Yes. Paying attention. No, it's the same. Y'all understood, right? You got them all? All right. Thank you. Congratulations. Thanks for coming and being participants in our workshop. Go. All right. As we invite our participants up, you'll get a chance to participate later on in our show. We call it a show? Later on in our training today. And so Barbara will make sure that you speak to Barbara after each of the presentations, and you'll get a chance to participate again a little bit later as we continue through our training. All right. Thank you, everyone. I'm grateful to have been part of our presentation this morning, and I will now leave. Thank you so much.
If you need translation services, please direct your attention to the screen for the frequencies. Si necesitan servicio de traducción, por favor mire las frecuencias en la pantalla. Now, please welcome to the stage, Dr. Brent Vaughn.
Immune system experts, right? Yeah. All right. So now it's my privilege to take you through what is the most exciting subject that everyone loved going through high school, right? Yeah. History? Yeah. That didn't sound very enthusiastic. All right, it's kind of a privilege for Dr. Parker and myself to kind of set the stage for you, if you will, on all the stuff that you're going to get from Dr. Wollmer and Dr. Groff. So you got an understanding of the immune system, but you also kind of need an understanding of where transfer factors came from and kind of how they got to where they are today. And so I'm going to give you that information so that by the time you get into Dr. Wollmer and Dr. Brock's talks, you'll have a nice solid base to help you understand and hopefully get more out of what it is they're going to share with you and just how exciting some of the stuff that For Life has done as well as just how amazing transfer factors are themselves. So let's kind of go through what we're going to talk about here. So transfer factors are not something that for life discovered or created. These things have been around since man has been around, and since any kind of complex life existed. They actually, something that was discovered in the 1940s. We'll talk about that whole process here in just a minute. We have, as you do the math there, that's about 75 years that transfer factors have been known to man, and 75 years worth of research, and that has amassed several thousand publications on transfer factors. Now in the 1980s, we found transfer factors in colostrum. Prior to that, most of the research, and in fact all the research, and all the understanding of transfer factors were those obtained from blood. And we'll talk about the differences between those as we go through this history. And then lastly, near the end of all of this, is the discovery by 4 Lives that transfer factors also exist in chicken egg yolks. So let's go back to the beginning. We're going to kind of go in a timeline-like fashion where just to kind of follow the history of transfer factors. So again, as I mentioned, this kind of starts in the 1940s. And at this time, a lot of researchers were looking for ways to kind of protect people from infectious diseases that can be transferred from one person to another. And there was one group of researchers that was interested in antibiotics, which we're probably all very familiar with. And so there was a group that was studying down that direction. But there was another group of researchers that were interested in more natural ways of activating the immune system, helping the immune system deal with these potential infections. And one of those was a man by the name of Dr. Florez. And in 1949, he was the man that came up with the term transfer factor. He was looking at these white blood cells. Now, Dr. Parker introduced you to the immune cells, and the white blood cells are those immune cells that circulate throughout your bloodstream. So it's all of those cells that he talked about, all kind of gathered together as they circulate through. And so he took these cells, and he said, what happens if we take them from one person and give them to another? Can we transfer immunity that way? And so on his first experiments, that's exactly what he did. He took white blood cells from one person, he injected them into a second person, and he was able to show that the second person then showed signs of immunity. And so he theorized that there must be these factors inside these white blood cells that could transfer immunity. And so he called them transfer factors. And in 1949, that was the first time that term was used. Now he continued his research and tried to further understand what exactly it was in these immune cells that was responsible for transferring that immunity. And so the next set of experiments, he took these cells, he ran them through some freezing and thawing a couple of times, which resulted in basically just breaking open the cells. And then he took what he got out of the cells, so what was inside them, and transferred those to another person and saw the same transfer of immunity. So now he knew it was something inside the immune cells that was responsible for it. A few years later, he took that one step further. Now he took what was inside those cells and he ran them through a series of relatively crude filters, essentially the same things they used in dialysis. And he was able to concentrate the contents of those cells down to these really small compounds that were about 10,000 Daltons in size. Now don't worry about that term Daltons, we'll talk about what that means in a minute. For now, it's just a way to measure really, really small things. And so he isolated these really small compounds and showed that those smaller proteins, these smaller compounds, were what was responsible for that transfer. And so that kind of gets us a lot to where we are today about how we think about transfer factors in terms of size and their function. So we kind of move in now to what we refer to as the middle period of transfer factor research. And a lot of things happened in this time. The researchers were looking for ways to better understand what transfer factors were and to kind of how to describe and characterize these compounds. And there was some kind of debate. Do we look at these and describe them based on their size? Now remember, at this time, they didn't have the technology that we have today. And Dr. Brock and Dr. Wollmer are going to introduce you to some of these technologies that weren't available at this time. And so, describing transfer factors by size was not ideal because they didn't really have a precise way to do that. So they thought, well, what about activity? Let's just describe it by what it does. And so there was this group of the researchers who thought, we'll go about it that way. And through this period then, you had them going back and forth as based on size, is it based on activity? And then what about dose? How much do we give? How do you judge how much is appropriate and make it consistent from one person to the next, or one study to the next? And so what they kind of settled on was we'll take 10,000 white blood cells. We'll break them open, we'll filter them out, and whatever comes through the filters there, that's considered one unit. And so that's how they decided to dose transfer factors. We'll give you 10,000 cells as 1 unit of transfer factor. And that's kind of how they standardized the therapy back in these early days. So continuing through this period, there was also some debate as to what transfer factors were. And some of the researchers thought, well, these must be proteins, or very small proteins called peptides. Others thought, well, maybe these are nucleotides. So that's a fancy word for basically pieces of your genetics. So are these little bits of DNA or maybe RNA? And others were still like, no, we don't have the technology to really describe it in either of those terms. We're just going to call it by what it does. So it's still kind of an activity-based description. And then also during this time, there was some still debate as to what size transfer factors were. Some of the researchers felt that it was even smaller compounds down around the 8,000 Dalton size. But there was other groups who thought they might be as large as 12,000, bigger. So there's still a lot of debate going on as to exactly what transfer factors are. So let's take a little bit of break from the timeline here for a minute and kind of give you some theories on what transfer factors are and how they're made. So what you see up here, the red circle represents an immune cell. And when it comes in contact with something that could be a threat, and remember Dr. Parker talked about the self, not self. So the cells identified this as something that is not self, it's not part of me. It will take it and ingest it and break it apart and kind of examine all the different pieces. And it'll look at those pieces and figure out which are some unique characteristics of this potential threat. And out of those unique characteristics, it will then make a transfer factor for 1 to maybe a dozen of these different unique characteristics. You kind of think of this as like the things you might see on a wanted poster. That is it the hair color? Is it eye color? Maybe it's a tattoo. So these are things that uniquely identify that threat. So this goes into that adaptive immune system that Dr. Parker talked about. We're now looking at specific things. We're looking for specific characteristics. So it will produce transfer factors, 1 or more of them, for each of these characteristics. It will then put them on its surface, and then as it comes in contact with other immune cells, it will transfer that immune knowledge to those cells. Now, it's also possible, and still yet to be understood, but these things may also be excreted into the blood, where they can float freely and come in contact with immune cells that are moving through the body via the bloodstream. So that's 2 potential ways that transfer factors are used by immune cells to transfer immune knowledge. So I mentioned that Dalton term earlier, and this is kind of a good way to help you understand just how small the molecules we're actually talking about. So we start off here on your left with an average-sized woman weighing about 60 kilograms. We go down about 60-fold there to a 1 kilogram melon. Now we're going to go down 1,000 times smaller to a 1 gram paperclip. That's not it. Another 1,000-fold change, we're down to the weight of a snowflake. Does everybody here held a snowflake? I only see a couple hands. Let's put it another way. If you take a single grain of rice, everybody seen rice? All right. You chop that single grain of rice up into 30 pieces. Each of those pieces is 1 milligram. So we're talking already pretty small, but that's not enough. Let's add 10 more zeros to that. Okay, so for those of you that are keeping score at home, that's 600 quadrillion times smaller than you and me. Who is that? Can we get security?
not the sharpest, but 600 quadrillion billion million? What does this mean? In real terms, please, Dr. Vaughn.
All right. Heaven forbid that we should have Calvin confused. Let's put it in other terms. 600 quadrillion. You go outside tonight, find a nice dark place, and you look up into the sky and start counting stars. By the time you've counted all of them in the Milky Way galaxy, you're still going to be short. 600 quadrillion is more stars than there are in our galaxy. So next time you go out and you're looking at the stars, I want you to point up at it and say, that's a transfer factor, that's a transfer factor, that's a transfer factor. Put it... To put it another way, each and every capsule of transfer factor products, regardless of whether it's trifactor, classic, or plus, contains trillions of individual transfer factor molecules. Right, do we agree that they're pretty small? All right. So also, as we're in this kind of middle period, they start looking at what can you do with transfer factors? How transferable are they? And they discovered that you can take transfer factors from a cow, and you can transfer them to a guinea pig, to a mouse, or to a chicken, and they have the same immune effect. This is unique. There's not many things that you can take from one person and give to another and expect it to function the same, let alone from one animal to a different animal and still expect the same effect. So that speaks to just how central transfer factors are to immune system function. They are key. They're something that is common across all mammalian and all complex immune systems. And this also kind of moves us into a transition period here as we move into the late 80s and into the 90s and beyond. As transfer factor research begins to kind of taper off a little bit here, especially in terms of those looking at blood. And we'll talk about that, some reasons for that in a minute, but the researchers at this time started looking, where else can we get transfer factors? And the thought comes, well, mothers transfer immune information from themselves to their newborn infants, and that must be done through the colostrum. And so researchers begin looking at colostrum as a potential source for transfer factors. And in 1989, a group of these researchers did a patent on getting transfer factors from colostrum. A few years later, this was the patent that David Lizzie came across and was what caused him to look at creating For Life and being able to take the information and all the research that they had amassed at this point and make a company out of it. So he licensed his patent. So as I mentioned, as we get into the 90s, the research on blood-based transfer factors begins to taper off. And the main reason of that is, you may remember in the early to mid-80s, there was a lot of scares that came up about the safety of blood. There was the AIDS epidemic that became widely known. There were issues with hepatitis and some other blood-borne diseases. And so researchers were less willing to play with blood and to look at it as a source of transfer factors, and were more interested in safer forms of it. And so this time period, these research shifts to looking at transfer factors from colostrum. It's also in this time frame that For Life discovers transfer factors in egg yolks. We'll talk a little bit more about that in a minute. The last thing I kind of want to point out here is this is the first time during this period that we have a researcher looking at what exactly are transfer factors. What is the sequence of amino acids within this molecule? And so one of the researchers makes the first attempt at this and kind of identifies transfer factors as being about 44 amino acids in length, and about a dozen of those amino acids tend to be consistent from one molecule to the next. So about 2/3 of it changes quite a bit, and it provides that specific information, and about 1/3 of the molecule seems to be consistent across all of them. So this is also the time period where, of course, For Life begins and introduces transfer factor in a commercial option. Up to this point, transfer factors were only available to researchers, and it was an expensive thing to produce. and wasn't available to anyone outside of a research institution. With the advent of For Life, we now have transfer factor in a number of options, and it was the first way that most people had access to these wonderful molecules. And as I mentioned before, at the end of this period, we get into 2003, For Life furthers the advancements in transfer factor science by finding transfer factors in chicken egg yolks and patenting the extraction of them from chicken egg yolks. All right, so that brings us to kind of summarize everything that we've talked about so far. First of all, transfer factors are not something For Life discovered. They've been around for a very long time. Dr. Lawrence first identified these things in the blood and found that they were responsible for transferring immunity. Since that time, so from 1940s all the way up to today, we have somewhere between 2,000 and 3,000 studies that have been published on transfer factors. That's quite a lot of research for these little compounds. In the 1980s, this research switched from blood-based ones to colostrum-based ones, which were For Life, kind of picked that up and carried it forward and brought transfer factor to the masses with the creation of the company there in 1998. And as we continued with that, in 2003, For Life furthered transfer factor science by identifying and concentrating transfer factors in chicken egg yolks. Okay, it's time for another volunteer. Anyone? It is new questions. We have a brave soul. Translation? Okay, so our first question. Which blood cells did Dr. Lawrence use to first identify transfer factors? A, cellulars, A, sangre. I know a little bit of Spanish, but not enough to be helpful. Okay, from which blood cells did Dr. Lawrence first identify transfer factors?
White.
En las células blancas de los...
Muy bueno, es correcto. Okay, now let's see if you're paying attention at the very end here. How many studies have been published on transfer factors?
2,000 to 3,000.
3,000.
¿Todos en 3,000? Hey, bueno, correcto. Very good. Give her a round of applause. That was well done. Muchas gracias. All right, thank you very much. Now we'll move on to section 3.
Ladies and gentlemen, please welcome back to the stage, Dr. David Wollmer.
All right. How's everybody liking it so far? Are we learning a lot? Okay. Well, we're going to learn more now. Okay? So we're in part 3. So what we're going to learn now is that For Life transfer factor is comprised of cow colostrum and chicken egg yolk. We're also going to learn that For Life transfer factor is made by the immune system for the immune system. And specifically, transfer factor is made by the immune system of cows and chickens, and that immune system, as Dr. Vaughn talked about, can be transferred to other mammals, other species. Okay? We're also going to learn about how For Life utilizes very special filtration procedures to extract out transfer factors from cow colostrum. Okay? And then we're also going to learn how 4Life better understands the transfer factor through characterizations using several tools like amino acid composition, size extrusion chromatography, and proteomics. Okay? Are you with me? All right. So let's first define and describe the source of transfer factor. Well, I just said it comes from what? Where does it come from? Cows and chickens, right? And colostrum comes from cows, is the first milk by the mother to the baby calf. Okay? And it's done in the late stage of pregnancy and then in post-lactation. And it's yellow in color. It's not white like milk, right? It's yellow in color. And it's important to point out here that when 4Life gets its transfer factor, it only takes a small portion. Most of the colostrum that the cow produces for the calf is given back to the calf, because calves need to have that colostrum in order to help their immune system mature. Okay? Does that make sense? Okay. Now that colostrum comes out in the first 12 to 16 hours, and it provides us a rich source of transfer factor. Okay? Now the egg yolk's a little bit different. It's the nutrient-rich portion. The egg yolk is the nutrient-rich portion of the egg, and its primary function is to provide food, sustenance for the embryo. And that's coming from chickens. And now, let's look at how transfer factors are made. So the ability of mothers to transfer immunity to their offspring has been well documented for a century, hundreds and hundreds of years. And that's in mammals as well as birds. But for mammals, that takes place either through the placenta or through colostrum. For birds, reptiles, and fish, that transfer process actually happens through the egg. Okay, so it's a little bit different. And what it does is it transfers these